1.4, definite integrals by trapezoids. Essential question, how do you estimate the value of a definite integral by dividing the region under the graph into trapezoids? So hopefully you've noticed that counting squares to find the definite integral can be quite tedious, and we all count squares differently. So another method to find the region under the graph is to basically divide that area up into trapezoids and then find the area of each one of those trapezoids. So I guess the first thing you're going to need to remember is what a trapezoid is and how to find the area of it. So a trapezoid basically has two parallel bases, but maybe the other two sides are not exactly the same, maybe they are, but you have two parallel bases. We're going to have a height, and that height's always going to be perpendicular to the base. We're going to have two bases, base 1, base 2. And so the way that we find the area of a trapezoid, in case you forgot, is that you take the 1/2, the sum of the bases, and then you multiply that by the height. So we're going to work a problem together where we need to use the area of trapezoids to estimate the area under the curve. We are going to do number 2 on page 22, and it's a walking problem. So Pace Walker enters an AIDS walkathon. She starts off at 4 miles per hour, speeds up as she warms up, then slows down as she gets tired. She estimates that her speed is given by the following function, where t is the number of hours since she started and v of t is in miles per hour. Now, in order to make sense of the problem, I always like to start off by understanding what my units are. And a way that helps me do that is by creating basically a graph. Maybe I don't even graph the whole thing, but at least I create my axes so that I understand what's happening with these units. So my vertical axis, v of t, is going to be miles per hour, and my horizontal axis, t, is going to be number of hours. All right, then I'm going to go through and I'm going to continue reading the problem. So for A, Pace walks 3 hours. Plot the graph of v of t as a function of t for these 3 hours. Sketch the result on your paper, and be sure your calculator is in radian mode. All right, so let's look at that. Now I'm noticing this isn't working out so well, so I'm going to try move this over here. I'm already in radian mode, that's awesome. So now I'm going to graph it. And, you know, time is not going to be negative. I only really need to go up to 3, so how about if I go a little bit past that to 4? And I'm not sure, I don't think she's going to walk negative miles per hour. And I don't think she can walk more than 10 miles an hour. Let's check it out. So here's my graph. And before I graph it, I'm actually going to create a table so that I have my data points nicely organized and so that I can see their values. Now, before I do that, I've done this problem before, so I know that we should probably read ahead a bit. So look at C. I want you to think about what our units should be like. What intervals should we use on our x-axis or on our number of hours? Should we go up by 1 hour? Should we go up by 2 hours? Should we go up by half an hour? So if you read C, it says estimate the integral in part B using 6 trapezoids. Well, that means that what we're going to do is we're going to take our horizontal axis and we are going to estimate using 6 trapezoids. So we're going to have a trapezoid here, a trapezoid here, and so on. Okay, so we want to break this up into 6 intervals. Well, if I'm talking about 3 hours, how do I get 6 intervals out of that? That means I have to basically go up by half an hour each time. So when I created my table, I went up by intervals. I changed my interval by half an hour. So I started at 0 and I went up by half an hour. And there's my table. And then I copied down those values. Because in the future, you're going to have options. Sometimes you'll have to graph things, but other times if you're just given a table of values, you can come up with the trapezoids just using this. I'm going to plot my graph now for A. Something like that. Okay, I think A is done. So let's move on to B. B says, explain why a definite integral is used to find the distance Pace has gone in 3 hours. This involves looking at your axes. So, and it goes back to that exploration that we did when we were exploring what 1.3 was all about. It has everything to do with, let's label B, what one of these squares represents. So one of my squares, well, the base of one of those squares is hours, and the height of one of those squares is miles per hour. Area of one box then, or one square, becomes miles per hour times hour, leaving us with just miles. Well, and this is the same thing as distance, right? So this gives us distance. I think that that's a pretty good explanation. All right, moving on to C. Estimate the integral in part B using 6 trapezoids. Show these trapezoids on your graph. About how far did Pace walk in the 3 hours? So instead of using squares, we are going to use trapezoids. So I am going to draw 6 trapezoids where my height is actually along the horizontal axis. The height of the trapezoid, and my bases are these heights that take me up to my output values. So sometimes they don't look so obvious that they're trapezoids. So let me just draw one of these trapezoids out here to the side. So the way I'm drawing them is so that the bottom here is going to be my height, right? So my height is going along this horizontal axis. And then the other two, the parallel sides, those are my bases, base 1 and base 2. So the way I get the heights of these bases, each one of these lengths here comes from your output values, right? Because the height of one of these bases is whatever that output is along the vertical axis. All right, and remembering that area of a trapezoid is 1/2 the sum of the bases times the height. I'm basically going to add up all the trapezoids. So I have a total of 6 trapezoids. Each one has a base, each one has a height, and that height is going to be half. Okay, so that's where I'm getting this height from, is down here along this horizontal piece. And then each one has 2 bases, and I get those from these pieces here. And so I'm reading my vertical axis to figure out what those base lengths are. All right, so, and I'll do one trapezoid at a time. Okay, so trapezoid 1, and I'm going to call this the sum of 6 trapezoids. So that's how we would represent that. I do half times the sum of 2 bases. So this base here basically goes to 4, right? So I look for my first output, which is 4. The next base is the second output, which is 4.6442. And then I need to multiply that by the height, which also happens to be half. Each height is going to be the same. So really you could factor out this 1/2 in the very beginning and just multiply everything when you're all done. But I want to show you how this is done piece by piece. So I'm going to keep on moving on. All right, so my next trapezoid, well, it's going to be 1/2 the sum of my 2 bases. So the first base here and the second trapezoid is really my second output, right? That 4.6442. And then the second base is really my third output here, which is that output at 1, which is 4.9854. And again, I need to multiply also by the height, which is 1/2. Okay, this is going to take up some room, so let's do the next one. So now I'm on to the third trapezoid. It's 1/2 plus the 2 bases. So the first base I've already used, it's the output at 1, 4.9854, plus the second base for that third trapezoid, which is the output at 1.5. So that's 4.8632 times 1/2. Plus, now I need to do my fourth trapezoid. Hopefully you're getting this. So it's going to be 1/2 times the sum of my 2 bases. So now I'm on my fourth trapezoid. So I'm going to use the first output, which is at 1.5. So that's that 4.8632. Plus now the output at 2, which was 4.335. And I'm going to multiply that by my height, which is 1/2. Okay, I've got 2 more trapezoids I need to write down. So I'm going to have 1/2. Okay, so I'm on my 5th trapezoid. Okay, the first base is going to be that output at 2, which is 4.335. Plus, and now that second base is going to be the output at 2.5. which is 3.6492. Multiply that by 1/2 because that's my height. And I've got one last trapezoid. Why don't you guys pause the video, see if you can get it by yourself. Okay, so I'm going to continue on. 1/2 times 3.6492 plus 3.1284 times another 1/2. So hopefully you're seeing that every single term here has 2 halves in it, right? So 1/2 and 1/2, well, that's really 1/4. So I mean, you could have, and I'm not going to rewrite all this out because that would be a lot for me, but you could have originally seen that happening, and you could have then said, oh, you know what, I'm going to just factor out 1/4. So you'd have 1/4 times this, times that, or plus this next set of parentheses, plus the next set of parentheses, plus the next set of parentheses. So I'm going to put in a quarter. I'm going to bring that out. Now that's 0.25. Put in a set of parentheses to say everything else needs to get multiplied by that 0.25. And now I'll start putting in the sums of those bases. So my first set of parentheses gives me the sum of the first bases. Plus 4. Oops, I forgot a set of parentheses there, so I'm going to need to go back and insert some parentheses. I'm going to now enter it into my calculator, and I'm going to do that using the method I was just talking about. So I'm going to basically multiply everything, the sums of all the bases, by a quarter. So I'm going to use, instead of using a fraction, I'm just going to put in 0.25, and I'm going to use two sets of parentheses here. Every set of parentheses from now on is going to be the sum of the bases for each trapezoid. And I get approximately 13.0206, which tells me that's approximately 13 miles. 13 miles is about how far she has gone. Moving on to D. How fast was Pace walking at the end of 3 hours? So at the end, how fast was she going? Well, we can just look at our table pretty simply and say, oh, well, at the very end, she was going approximately 3.13 miles per hour. And when did her maximum speed occur? What was her maximum speed? So we're going to get a little bit more specific here. A couple ways we can do this, but I really like it with a graph. Let's see, so let's graph it. And I guess our question will be, where is the maximum? So we need to calculate our maximum, which is 4. And that's going to be that's not our left bound, so left bound needs to go to the left a bit more. Okay, I'll press enter for there. And I need to be right bound somewhere over here. And I need to take my best guess. Somewhere in the middle. Alright, so the maximum happened when time was approximately 1.12 hours. And her fastest pace was then 5. We can't get that information just from the table. We had to do a little bit more investigation. So we can say at 1.12 hours, she reached 5 per hour, which was the max, or her max speed. The last thing we'll go over is how using the area of trapezoids to estimate the area under the curve sometimes can give you either an overestimate or an underestimate of that area under the curve. So let's take our first example. If our graph is concave down, well, let me draw a couple of trapezoids here. So how about if I use this point and this point? So if I draw a couple of trapezoids, you can see that for the most part my trapezoids are underneath this curve and they're not completely rising to the curve. So anytime you have a concave down graph, using the trapezoidal rule to estimate the area under a curve is usually going to give you an underestimate of what that area actually is. Now concave up, on the other hand, so if I choose a couple points here, right, if I'm going from this point up to this point, notice how I'm above this curve, or really close to being on it. So concave up is usually going to give you, or is going to give you, an overestimate of the area under the curve. So how do you guys think we could make any of our estimates of the area under the curve using trapezoids more accurate? So think about that for a second. How can we get more exact results using the area of these trapezoids? Well, what if we made more trapezoids? So we had smaller and smaller and smaller trapezoids. That would probably reduce some of these inaccuracies, right? So if I made my trapezoid maybe this big instead, right, I'm kind of getting rid of some of that underestimation. So the more trapezoids you use, the more accurate your results are going to be.